Okay. One second. Right, okay, my audio's all fine. Okay, well, I'll get started. So, oh yeah, so there was last time, right at the end, we were talking about space-time diagrams and this trying to show time dilation from it. So I didn't have a lot of time, to be honest, to work through this particularly, but we can have a go at it. So I think really the way to do it is by thinking about the space-time interval and its invariance. So the way I thought that we can do it is not the most satisfying way. Actually, it still feels a little, I don't know. It feels like there should be a more satisfying way to do it. But anyway, let's do it this way by thinking about the space-time interval. Okay. So let's draw the same setup we had last time. We have a person A here who will measure distances from themselves as this length xa. And they have some clock to measure times, and we call this time coordinate TA. And remember, we had this other person that was on some sort of train or cart or something, which imaginatively we're going to call person B. And they've got their own clock, but at the moment this is drawing from A's perspective. So I just want to draw what person A will see. Okay. And this whole contraption here, well, I should say actually also we're using a light clock. You know, we like using these light clocks in special relativity because they give quite a natural definition of a tick, as these light beams bouncing in between two plates. And this entire thing, this man and the light clock, is moving to the right with some speed v. So what this chap here will see, person A, if we draw a second snapshot of what they'll see, to them the light ray will appear to be moving in a zigzag rather than just in a straight line. Okay, so this is from person A's perspective. This is kind of following on from what we did right at the end last time. So if you're unfamiliar with this light clock, you can, if you like, you can watch the part where we were talking about this in last, was it Friday? Yeah, last Friday's office hour. And that's on my YouTube if you want to take a look at that. So this is what person A sees. And now let's think about this from the perspective of person B. So from the perspective of the guy that is on the train with the light clock. Okay. So from their perspective, of course, they're standing still. There's no such thing in relativity as absolute velocity, absolute motion. There's absolute acceleration, but no such thing as absolute velocity. So just as A can say, well, I'm standing still and B is moving, they're the one moving off to the right with a certain speed, B is just as correct in saying, actually, I'm standing still, and it's A that is whizzing off to the left with some speed v. There's no distinction between the two. Okay? Neither one is more right than the other. I mean, obviously you could say, well, we can see A's wheels moving, but I mean, hello. Hi, Theoretical Phys 77. Good to see you. Okay. So now, person B will make measurements from themselves. They will measure lengths that we'll call x, b, and they have their own clock. I mean, technically their clock is the light clock, but, you know, imagine the light clock is plugged into their clock, so they can read it, because a light clock is probably not very good for actually making sure you stay on time for things. And this measures time. TB is their time coordinate. And what person B sees in terms of the light clock, they see the light just moving up and down between these two parallel plates. They don't see this zigzag that person A sees when they're looking, okay? So this is from person A's perspective up here, and this is in person B's perspective down here. So we can draw this on a space-time diagram. Now when I draw the space-time diagram, I'm going to draw the second bounce of the light as well. I'm going to draw it where it starts at the bottom, goes up to the top, and then bounces back down. So when I draw this on the space-time diagram, I'm drawing in this line too. The only reason I'm not drawing it here is because I've run out of space. But you can imagine the light is now going to zag down. This is the zig, this is the zag. Down back to where it started, okay? So we have sort of three events. We've got the event where the light leaves the bottom of the light clock. We've got the event where it reaches the top and will bounce off. And we've got the event where it reaches the bottom again. We've got these three distinct points in space-time. So let's draw these on person B's space-time axes. Good evening, Marmite Pasta. Interesting name. I like Marmite and I like pasta, but I don't think I've ever combined the two. So let's draw these three events on B's space-time diagram. So the light starts off at the origin. We should also say, actually, in doing this problem, we're going to synchronize the origins of these two. So at the instant that person B starts their watch and person A starts their watch, they're sort of on top of each other. Maybe person B's train is right here when it starts off. So they have the same t=0 coordinate. Then the light will bounce up here. That is this zig, this part here. And then it will bounce back off of the wall here, back down to the bottom. So these are the three events as shown in B's space-time diagram. Okay. Well, now let's try and draw things from A's perspective. So for A's space-time axes, I'm going to use green axes. Okay. TA and XB. So we said that the axes start off coordinated. So this first event where the light is leaving the bottom is synchronized in both frames. Okay, the light pulse is released when person B is on top of person A, and they start their watches all at the same time. Okay. And now the light will bounce off again, and it has to bounce still at a 45-degree angle, because this angle is what indicates the speed of the light ray. And light, this all comes from the fact that light travels at a constant speed to both people. They both see it at the speed of light c. This is where all this sort of weird behavior comes from. So the light bounces off like this, except now it doesn't actually come back all the way to x is 0. This third event is actually here. It's no longer along the TA axis, which you can imagine if you think about the XA position, the position that that person A will measure for these events. He measures this event here at XA is 0. This happens at his feet when these are all lined up. But then because the train is moving to the right, this event here where it bounces off the top plate and where it comes back to the bottom plate, these don't happen at the same position because the train is moving from his perspective. Okay. And if we sketch the TB axes on this diagram, well, the TB and the XB axes, these will look like this, where this angle theta, I got it wrong last time, I said tan of theta was equal to 1 over v, but actually tan of theta is just the velocity of the train, okay? So what we were trying to do last time was we were trying to compute, well, we sort of drew this length to here, and we were trying to compute this length in terms of this length, and say that that gave a relation between the two. But I think that there's a flaw with that in that the scaling of these axes is not the same. So the whole geometry of this is not Euclidean geometry, it's a little bit more complicated. So rather than thinking about lengths as, you know, kind of Pythagorean x squared plus y squared lengths, the metric actually has a different sign. So when we're finding lengths involving the time coordinate, this will have a minus sign in front of it, which is this metric that gives us this Minkowski geometry. So if we take as a given that the space-time interval is invariant, which I define like this, then we can think about what this interval looks like in different reference frames. So on B's coordinates, you can see that the interval between this event and this event has a time difference, certainly. We can say that this time here is delta TB, but there's no difference in x coordinate as measured by B. Because remember, B is moving along with the light clock. They're on the train next to it. They see no distance between this point and this point because the light just bounces straight back to where it started out. So for this person, the space-time interval is just given by minus delta TB squared. Okay. So that is one important equation. That is the space-time interval as measured by person B. And then according to person A, well, now there's a time difference between these 2 points, and there's also a space difference. So given that this angle here is theta, and we have this relation that tan theta is equal to v, we can use that to find this length here, this horizontal length underneath this point. So this length here, the time that is measured by person A, we just call delta TA. That is the TA coordinate of this point. But we're interested in the XA coordinate. In other words, what this length here is. Okay. So I mean, you could think of this as you could find it using the angle. You know, you could say that X, oh, sorry, I've just realized that here, this should be an A. It's in green, so you probably read it like that, but that should be an A. Okay. So you could say that XA is equal to tan theta delta TA, delta XA, that is, sorry, this length here. And that simply just gives us v delta TA. So I mean, messing around with the tan theta, you didn't really need to think of anyway. It's just velocity times time. Okay. So if you compute the space-time interval in this frame, we have delta s squared as measured by A is given by minus delta TA squared plus v squared delta TA squared. So that is our second expression for the space-time interval. And because this interval is invariant, all we're saying is that the expression for the interval here is equivalent to the expression for the interval up here, which just means we have delta tb squared is equal to minus delta ta squared plus v squared delta ta squared. Or rearranging that, delta ta squared is 1 over 1 minus v squared. Delta tb, sorry, I've got rid of the square here, okay? Which is the formula we wanted. This is the time dilation formula that we derived in a slightly different way last time, okay? Of course, here we've set c equal to 1 implicitly, but if you did it any differently, you would instead just have that these axes would all have a factor of c, therefore tan theta would be v over c, and then you would just pick up these extra c's, and it would come out that you would have it as 1 minus v squared over c squared. So there's nothing to worry about there. But yeah, this is still a slightly unsatisfying derivation for me. There's probably a way you can do it, I don't know, just by geometric construction, but maybe there isn't. Well, I'm sure there is, I don't know. I know there was something about you can use invariant hyperbole to find the scaling on the axes. That's probably a nicer way to do it, but yeah, like I say, I didn't have too long to think about this, so this slightly more straightforward way is how I chose to do it. Okay. Then I had a nice email question from somebody on my website, and it's sort of a question in two parts. So they say that they are currently a master's student in physics with, oh hello Jake Chin. They're a master's student in physics with a bachelor's in engineering from a decade ago, and they have a choice to potentially take a bachelor's in physics as well based on what they've already done, though it may require a few extra courses. Their question is it really worth their time to squeeze a bachelor's in physics out as well, even though they're already on track to earning their master's within the next year? They'd like to do a PhD afterwards, and if all goes to plan, they should have some summer work experience as well to beef up the CV. So this is a little unfamiliar to me, because in the UK setup, you can't sort of take extra courses to turn, you know, like we can turn a bachelor's of engineering into a bachelor's in physics. So I guess I don't know what would be involved for you in turning this engineering course into a physics course or changing it into a bachelor's in physics. But I mean, if it doesn't cost money, you know, if you're already enrolled as a student, I suppose I'd wonder why, I don't know, I mean, why wouldn't you, I suppose, if there's no downside to it like that. But of course there may be. I'm not entirely sure, because it sounds like it's a different educational system than to the UK. Certainly there are differences between an engineering degree and a physics degree. But if you're already doing a master's in physics anyway, it seems pretty unlikely that you're going to be missing out on much material that would be covered in a bachelor's degree. I mean, I suppose it depends what kind of master's you're doing, how specific it is. Because you know, if you do a master's in something like, I don't know, like a research master's in very experimental particle physics or something, it's possible you could miss out on some physics if you didn't have an undergraduate physics degree. Maybe there's some formalisms of electromagnetism and stuff you haven't studied. So it's possible there might be some undergraduate material that would be useful. And if you're applying to grad schools, you know, they'll ask for a list of all your courses and transcripts and stuff. So, you know, it's plausible that if you had some major holes in your education, that might be a problem to someone. But then they ask a second part of the question, which is a little technical. Well, which is, sort of a technical particle physicsy question. So I'm assuming you don't have many holes in your knowledge, actually, based on, if you're studying things about neutrino mixing and quark mixing and the CKM matrix. I'm sure your knowledge is probably pretty good for undergraduate physics, so that doesn't sound like it would be a worry. And yeah, it's definitely a good idea, as you mentioned, to get some summer work experience. I assume by that, do you mean like research experience? I mean, I don't know. This person may not be listening, but I mean, if they did mean research experience, that's particularly good when you're applying for PhDs. So yeah, I hope that answer helps a little, but it's hard to say. I suppose in general, I would say if you're doing a master's, and if you're doing it in a pretty technical area. Oh, you are listening. It's you. Oh, okay, right. Sorry, I didn't know. Then I'm sure it's fine. If you're doing a master's and you're doing it well. So I don't think it would be an issue. But that's just my, obviously this is coming from the perspective of someone that is a student rather than, I have nothing to do with admissions. I don't know what conversations go on there. So yeah, it may well be different, but I would imagine generally people only really care about, once you've got a degree, people don't really care about your high school qualifications so much. Once you've got a master's, they don't care so much about your undergraduate degree. Once you've got a PhD, generally it's the most recent thing that is most important. Oh, the CERN summer school program. Oh, cool. Oh, well, I hope that works out. That'd be great. Yeah, they all got cancelled last year, which is kind of sucky. Yeah, that's fantastic if you can get onto that. Then you also asked a question about the differences between quark and neutrino mixing. They say quarks do not oscillate, and I get the impression that the quark states are not actually mixing in the same way. Rather, the CKM matrix is more of a mathematical adjustment to make calculations easier. How does this map onto what is happening in reality? Well, so this all comes from the fact that in weak interactions, interactions are described between flavour eigenstates rather than mass eigenstates. So, in the strong interaction in QED, interactions happen between mass eigenstates of particles. But in the weak interaction, it's different. They happen between this weak eigenstate, which is in general, you can think of it as like being expressing, well, it's like, if you think about a vector is a more abstract thing than defining as components and basis vectors. You can define a vector in as many different coordinate systems as you like. You can just take your coordinate axis and rotate it. It's just a linear transformation. The components are of each other. And it's similar for these different eigenstates of these particles. So the mass eigenstate is in general a linear sum of the different flavour eigenstates and vice versa. So as far as I know, it's the same kind of thing that's described between them. The CKM matrix and the other one is like the I don't know, whatever the one is that describes neutrinos. It's like PMS, PMSN or PNN. There are some letters, I don't know. It's neutrino physics is not my area. But because of that, as far as I can tell, actually, I think quarks would have the same kind of oscillation. That's it, PMNS. I think quarks actually would oscillate in the same way as neutrinos do, but I think it's because of the other interactions between quarks that aren't present for neutrinos. So neutrinos only interact via the weak interaction, whereas quarks interact by the strong interaction, EM interaction, and the weak interaction. So if you have some like a weak interaction process that produces like a flavour eigenstate of a quark, or where you're considering flavour eigenstates of quarks, as soon as there's any kind of like strong interaction or EM interaction involving the quarks, it's like that. It's like the wave function collapses again. It goes back to the mass eigenstate. Would be my understanding. Whereas for neutrinos, because they don't interact via the strong force or the EM interaction, they don't get collapsed in that way. They can just kind of stay in a flavour eigenstate, and they can, therefore they can have these oscillations. Whereas quarks don't have the opportunity to have oscillations because they're also interacting strongly. And of course you can't have free quarks because quarks are confined. There's never any opportunity for quarks not to be interacting strongly because they're always bound. They're always interacting strongly in ordinary matter. Therefore, I think they're always in a mass eigenstate. So this flavour eigenstate, it doesn't really get a chance to exist and evolve. So the neutrino oscillation, I think, it comes from if you take a neutrino in a flavour eigenstate, then just like in ordinary quantum mechanics, you can time evolve it. And when you time evolve these things, there's a phase factor in front of them. It's like an e to the I, it's like in quantum mechanics when you have an e to the I et or something for a time evolution. So if you prepare it like in a pure mass eigenstate, which is a sum of these flavour eigenstates, then these components that are the flavour eigenstates will evolve according to this. Oh no, sorry, is it the other way around? If you prepare it in a... Yeah, no, I think it's the other way around, sorry. So if you prepare it as a flavour eigenstate, which is a sum of these mass eigenstates, it's the mass eigenstates that evolve, according to like a sort of e to the I et term, like this phase factor. And if there's a difference between the masses of the neutrinos, then this phase factor is different. The E is roughly the mass of the neutrino or something in the rest frame. So if these different components that make up the flavour eigenstate, that are the mass eigenstates, you've written your flavour eigenstate in the basis of your mass eigenstates. If the phase factors on these mass eigenstates are evolving differently, because the different neutrino mass eigenstates have different masses, then you no longer have a pure flavour eigenstate by the end of that. The different components are sort of rotated a little. So if you come to make, like a measurement, or you do some interaction that involves a weak interaction, it doesn't happen purely between single flavour eigenstates, because now you no longer have a pure flavour eigenstate. You have something that is in general a sum over them, because the coefficients in front of the mass eigenstates that you've written your flavour eigenstate in have evolved differently. And I think they use this fact to justify why neutrinos have masses, because if neutrinos didn't have masses, then there would be no relative phase between these components that make up the flavour eigenstates, or these coefficients in front of the mass eigenstates, sorry. So based on the fact that you can see these oscillations, from solar neutrinos and stuff, you can infer that there is a difference between the masses of neutrinos. I think actually, like I say, I don't know a huge amount about neutrinos, but as far as one of my friends was telling me quite a while ago, I think the accuracy with which we actually know the masses of the neutrinos is pretty non-existent. I think the thing we really know is just the differences between the masses, rather than the masses themselves. But as I say, I'm not too well up on that. But yeah, so as far as I know, that it's the same kind of thing, and actually quarks would show oscillations, as far as I can tell, but it's because they also interact via the strong and the EM interaction that you don't hang on to these pure flavour eigenstates. They, when it interacts via the strong force, they will turn into like a mass eigenstate. If that makes some sense, that's my kind of way of thinking about it. And yeah, I think I actually misread your question when I first looked at it. I thought you were talking about how do you. Oh, you're welcome. Oh, I'm glad you got something from it. I think I misunderstood it at first. I thought you were asking about how do you kind of picture neutrino oscillations, like as a physical thing, and that got me thinking along much more kind of philosophical lines about that. Because I think actually you can't picture those things really. There's no sort of natural analog to the what we observe in the physics on our length scale. I think it's the distinction between understanding and kind of understanding through formalism and mathematics. So like, if I'm going to throw a ball or something, or pick up an egg, even something as simple as that, I have a sort of natural physical understanding of, how much force I can apply so that the egg doesn't shatter, or that the ball doesn't just crash to the floor, that it goes where I want it to go. Which is something that doesn't rely on, when you pick up an egg, you're not doing calculations where you're thinking about the stress-strain properties of the eggshell and the tension your hand is applying and stuff. It's just an instinctive thing. But when you get to more complicated things, say you're trying to calculate the trajectory of a rocket in orbit around the Earth, then that's something that you don't have a kind of natural intuition for, even though that is technically just classical physics. So I think there's an interesting distinction between understanding that is sort of instinctive and inbuilt, and understanding that is reliant on mathematics as a crutch. And I think all understanding, when it comes to things that are on that scale of fundamental particles and quantum mechanics, is totally reliant on mathematics as a crutch. But that's not to say you can't build up intuition, but it's more like intuition for results that are confirmed through the formalism, or intuition for the formalism. Yeah, no, I knew that wasn't what you were asking, but I think when I read it earlier today, I misread it, and I was thinking about that, and then I realized, oh no, wait, it's a perfectly well-posed, well-defined particle physics question, not a philosophically one. But yeah. Okay, cool. There was another brief question that I saw on Reddit that is a kind of straightforward calculus question. Well, not straightforward. I mean, it's just a calculus question. So I'll go through that. But then after that, that kind of brings me to the end of things that I've got in advance I wanted to talk about. So if you do have any questions in the chat, please do. Oh yeah, could we do length contraction? Oh yeah, sure. Yeah, good idea. We can talk about length contraction. So this person had a differential equation that looked like this. And I think they were struggling to solve it a little bit. So differential equations like this are quite nice in that there's a trick you can do to solve them most of the time. So it's a similar trick actually to the one we used when we were working out the precession angle for Mercury, where we did a substitution and then, well, actually no, I suppose it's not quite similar. I mean, the idea is that something will cancel. I think what you can do with this problem is you can write, or you can consider taking the derivative with respect to, well, I'm going to assume these primes are x's, of y prime all squared. Okay. And then by doing the chain rule on that, you find that this is just 2 y prime, y double prime. Okay. So you can rearrange that if you like as an equation for y double prime being 1 over 2 y prime derivative of y prime squared dx. And then if you put that back up into here, we end up with 1 over 2 y prime dy prime squared by dx minus y prime squared minus 1 is 0. Now is this going to be straightforward? This might not actually be straightforward. Maybe we should have used y prime cubed. If you used y prime cubed, then you just get a y prime squared here. Then that's a y prime to the 4th. And that, oh no, that's not better. That's a lot not better. That is nonlinear. Maybe this differential equation is not as straightforward as I thought, actually. So then you've got dy prime squared dx. Hello. Minus 2 y prime cubed minus y prime. Okay, actually, this is not a straightforward one. Yeah, I think I misread this one. I think if this was a... No, actually, yeah. I'm not entirely sure how you solve this differential equation, now I think about it. Yeah, I think I jumped the boat on this one. Does anyone else have any ideas how you could solve this differential equation? I mean, we basically just got a substitution where we've replaced what we're thinking about y. Oh no, wait. Oh no, this is fine. Sorry. Yeah, I'm being really slow today. So all we're saying is that y prime squared is equal to u as a new variable. So we just have du dx minus 2. Well, okay, maybe it's not actually that straightforward again. Well, I mean, it's not as bad as it was before, but now it's, du by dx is minus 2u to the 3 over 2 minus u to the half is 0. Now this is a separable one, so you can write it as an integral just over u. But actually, no, you can't. Sorry, it's not. You can't write it like that. No, yeah, this is probably a tricky one. Threw me for a loop. That's okay. Oh, well, thank you for saying it's interesting, but I mean, I also have no idea how to do this one at the moment. Why is it not separable? Well, because separable ones would, if it was something like this, du by dx times this was equal to 1 or something, then you could separate it. But I mean, here... Oh, you know what? No, I am being really slow. No, you are right, actually. I don't know what's going on with me today. So I can just write this as 2u 3 over 2 plus u half. Yeah, sorry. That's my bad. So this is all du over 2u to the 3 over 2 plus u to the half equals dx. I mean, now we've just transferred this problem into possibly an equally difficult problem of doing this integral. But at least there's a slight light at the end of the tunnel. So is that an integral we can do? Well, would it help to write it as this? 2u cubed plus 1. Possibly not. Yeah, I'm not sure if that is a if that is an integral that we can do. Not cubed. Oh, sorry. Yeah, of course. Yeah, thank you. Although it still is, it's slightly easier, but yeah, you're right. U to the 1. It's slightly easier, but still not straightforward. How would you do that integral? Does anyone have any suggestions for this integral on the left? Don't know. Maybe there's a clever substitution you could pick, but I'm not sure. Yeah, I mean Wolfram is Wolfram is the default. Yeah. It looks like it doesn't look so horrible that it doesn't have an analytic solution, but I can't think how you would get to the. You can do the you can do the one on the right. Oh, great. Thank you. Yeah, it's the one on the left that is causing the most bother. Yeah, nothing is jumping out to me about how you would do that. U equals cos squared x. U equals cos squared x. That'll be 2 cos squared x plus 1, which is, well, that'll turn into like a cos 2xy term, won't it? Minus 1 or something. Tan squared x. Yeah, I don't know. It's not obvious those things would work. Yeah, I'm not sure. That's the sort of stumbling block, I guess, with this problem. I mean, what about no something even as simple as like v equals u to the half? Well, no, actually, because then when you differentiate that, you'll still just get a square root term, but then it'll be on the top, won't it? You'll get like a dv is 1/2 u to the minus half. Oh no, actually, maybe that'll work. Du, so that's 1/2 1 over v du. So du is 2v dv. So then the integral becomes 2v dv over v 2v squared plus 1. Oh, well, okay, that's fine. Why didn't we think of that earlier? Unless I've made a mistake in the substitution, but if I haven't, that's a perfectly fine integral to do. We should have guessed that substitution much earlier. Yeah, that all looks okay. dv is 1/2 u to the minus half du, which is 1/2 1 over v du. So du is 2v dv. Yeah, okay, that's fine. All right. So then we've just got to do the integral with respect to v of v squared plus 1/2. And that'll give us x. And that is, well, I can never remember these integrals. Is this the arc tan 1 or the arc sine h1? It's one of them, isn't it? So then you'd use a substitution like v equals 1 over root 2 tan. And then that would give you a sec squared on the bottom. For dv would give you another sec squared on the top. So yeah, it'll be arc tan. So what, we get x plus c. And then on this side you get arc tan. Yeah, that's it. 1 over a. Yeah, so it'll be root 2 arc tan x over root 2 or something. Oh, sorry, v over root 2. Possibly I've got the a the one way around. I can never remember how it appears. Oh, well, it should be root 2v here, shouldn't it? Does that work? Leave you. Why can't I write today? Root 2v. That's what I mean. I think that's okay. Then that means that v is equal to 1 over root 2 tan x plus c over root 2, I believe. And then remember, v we called u to the half, so u is just that squared. And then u was equal to y prime squared. So, maybe we should have just used the. No, that's fine. That's fine. Yep. So y prime squared was u, and v was u to the half. So that means y prime squared is 1 over 2 tan squared x plus c over root 2. And then we just square root again. So y prime is, well, I guess now it's a plus or minus, or let's ignore that, is 1 over root 2 tan x plus c over root 2. Yeah, and then we just have to integrate that again. So then y is going to be what's the integral of tan? It's something weird, isn't it? Like log sec. I think it's log sec. If it's log sec, yeah, thank you. So that'll be natural log of sec x plus c over root 2. Hang on, what prefactor should it have? Still the same, 1 over root 2. And then plus d, some integration constant. And then I guess you just need to find these constants. Well, that's okay. So as far as I can tell, that's the solution to that problem. First it looked easy, then it looked hard again, then it looked easy, then it looked hard again, and then it turned out to be okay. So it's a lesson in perseverance. Okay. Anyway. Oh yeah, so is there a constant missing? No, there shouldn't be a constant missing. It was second order. So this is the constant from integrating tan x. The d here. This is where we get, this is from doing this integral with respect to x. That's where I drew this d. Okay. Oh, or do you mean a constant as in the c here? Ah. No. No, I don't think that the c. If you mean the c, like the constant coming out the front here, I mean the constant here you get. No, I don't think so. Yeah, so but this is the constant from integral of tan x equals sec x. This is the integration constant here on the end. It's this plus d. Okay. That's what I mean by this d. Oh, that reminds me, another thing. I noticed today that I have exactly 137 followers, which is a pretty exciting number in physics. If you know about the fine structure constant and physicists' kind of obsession with it, that is exactly 1 over 137. So I felt like I should just mention that regardless. because it's a pretty nice number. Integral of tan 2x equals 1/2 log of sec x. Odds that an electron will absorb a single photon. Well, the fine structure constant is related to that kind of thing, finding those scattering processes. Funnily enough, yeah. Integral of tan 2x equals 1/2 log of sec 2x. Well, if you differentiate log of sec 2x, you get a the derivative of sec times 1 over sec 2x. What's the derivative of sec 2x? That is minus would you also divide by the 1 over square root 2? Maybe we should. Yeah, I guess you should actually. Yeah, I suppose you will get an extra 1 over root 2 out from doing the chain rule here, won't you? So yeah, I suppose we should get rid of the log of that here. Ah, I see what you mean now. Yeah, no, that's I think that's correct. Yeah. Yeah, thank you. Okay. Yeah, then you also mentioned, someone mentioned about length contraction. So deriving length contraction is similar to deriving time dilation. There's sort of two sides of the same coin. Often when you're trying to resolve some apparent paradoxes in GR, when one person sees a time dilation, the other person sees a Lorentz contraction, a length contraction. And that usually comes into how these paradoxes are not actually paradoxes. They're actually perfectly sensible things. So let's try and derive it using space-time diagrams again. So let's consider the same setup we had before. Let's remind ourselves where perhaps now instead of a light clock, we consider a rod lying on this train. So let me copy this. Let's get rid of that for a minute. So we've got this same setup, but now I'm going to get rid of the light clock and replace it with, well, let's get rid of him too. Replace it with a rod of some length. Whoa, that's not a rod. Okay. Like this, or a log, maybe, why not? This is a train that's transporting lumber. Okay. So, how do we think about the length of this rod? Oops. Well, for person B, it's pretty straightforward. The rod is just still to them, so they measure the length of this rod as the difference between the spatial coordinates of its ends. You can consider the two ends of this rod as a space-time event, where person B will measure these two ends simultaneously because they're in their rest frame. So we're going to call the length of the rod L. But for person A, it's slightly more difficult. Because simultaneity is lost in relativity, person A actually can't measure the ends of this rod simultaneously. So they will see, again, these two events here that correspond to the either end of the log, but because the thing is moving, they won't be able to measure these two ends of the rod at the same time, because these events is drawing so pretty also a prerequisite? Wow, you think my drawing's pretty? Crikey. Thank you very much. No, I think it's helped by the iPad. One of my friends pointed out the other day when I showed him something I'd written down. He was very shocked that either my handwriting had got better or the iPad was doing some kind of magic for me, and I think probably it is the iPad. I have a good bow tie collection. Well, I've only actually worn this single one on stream. I wear the same one every day pretty much, and this one has got bumblebees on it. I do have a few more though. This is not all of them. This is a small selection. I like this one because it's got squirrels on it. I don't know, can you see the squirrels? I assume so. But yeah, I do like bow ties. I have, if you include all my ones at home, I have got something like 130 now. It's a little bit of a obsession, but weirdly I only wear this same one most of the time because I like the bumblebees. Okay. So yeah, because the two ends of this rod can no longer be measured simultaneously, this will affect the measurement of the length that person A sees. So let's draw this on a space-time diagram. So person B, the person that is moving with the rod, they're the easiest to consider first. Because for them, the rod, at the instant we measure it, has a single fixed time coordinate. Okay. So here is XB, the position that person B measures, and TB, the times that person B measures. And they measure the interval between these 2 points, delta XB, as L. Okay. Good suspender collections. I have like 2 I wear frequently. Where did you hear that? How did you hear I had a collection of... Well, I shouldn't say suspenders. Suspenders are more like those things that strippers wear. Suspenders are what do we call them? Braces is the better word. Like these are braces. Things that hold your shirt up. Those are... I call them braces, not suspenders. But yeah, I have a couple of pairs. Okay. Now let's draw TB's frames. Sorry, let's draw all of this in terms of TA's coordinate system. So again, I'm going to use green for person A. And remember, when we're drawing person B's space-time axes on person A's axes, we draw them like this at an angle. Where this angle theta is related to the velocity of B as measured by A, like this. So now you can see that the two ends of the rod, which were simultaneous to person B, are no longer simultaneous to person A. There's now a difference in the time between them. Okay. So again, we can use some straightforward trigonometry. And we need to use something else. The thing we'll use, just like we did when we showed the time dilation formula, is that the space-time interval between any two events is invariant in any reference frame. So the space-time interval, remember, is given by this expression for just motion in one dimension. So the space-time interval measured by person B only has a spatial component. It has no temporal component. So is just xb squared, which is L squared. Well, it's not that you can't measure the length of it. It's just that when you measure the length of it, because there's the distance between these 2 points, you can't measure the length simultaneously. So it's like, you know, if the log is straight in front of me, I can snap my hands down and touch both ends of it and say the distance between these 2 points I've touched is the length. But if the thing is moving, or rather if I'm moving with respect to it, so if you imagine I'm moving, well then because there's a difference, it's like the difference in the spatial positions of my hands, because there's a motion here, the difference in spatial position, when you transfer into the frame of a log, corresponds to a difference in temporal positions. So instead of me putting both my hands down like that to measure it, I end up kind of putting one hand down first and then the other. So instead I kind of measure, it feels like I'm measuring a shorter length of the rod than I actually am. I'll be honest, it's a little hard to picture. And it's even harder to explain. And you know, I don't pretend to have the most natural understanding of it, but that's my understanding of it, is that when you're in motion, the temporal distance between your hands, if I'm using my hands to measure this log, they pick up a temporal difference between them from the spatial difference. The garage door picture helped. What do you mean the garage door picture? What, like, I'm trying to think what you mean by that. Yeah, I'm not sure. I mean, it's the same sort of logic that solves this ladder problem. I think I hadn't heard it called the ladder problem, but someone else mentioned it on the stream. I'd seen it as like a train problem, and I think I talk about that in possibly the second office hour I did. I can't remember, where you've got a train that is trying to get through a tunnel where they close at some point the doors on either side of the train tunnel will shut very suddenly, and from the perspective of the person that is not on the train, they see the doors shut at the same instant, but they also see the length of the train contract. So that means the train is short enough such that when the doors slam down, the train is fully inside of the tunnel, so it doesn't get cut in half. And from the perspective of the person on the train, the spatial distance between the two doors, from the perspective of someone that is standing, say, just outside the hill or outside the doors, will see them close simultaneously. From the perspective of the person on the train that is moving towards them, they don't see them close simultaneously. They see them kind of close, you know, first one first, then the train can get in a bit more, second one after. So the train, even though its length to the person on the train is longer than the hill itself, it doesn't get cut in half because it looks like the train is cutting, the doors are closing separately. Oh, it's the same thing. Oh, it's a garage with a door at east end. Yeah, exactly. It's that same problem. That's the kind of intuition I'm thinking about it with. Basically the train thing. Oh, okay, yeah, I haven't heard of that before. Is it because of the diagram that the log is diagonal, so it's not possible for A to measure the log at the same time? Yeah, that's exactly it. It's because, if you like, this length here, measuring the length of something at the same instant of time is what we call the rest length. You know, it's when something is sat still in front of us. You can measure the length of it very easily because you know exactly the position one end is and you know the position of the other end. But when it's moving, measuring it simultaneously is no longer possible either end, because the distance, the spatial distance between either end of the log will correspond to a temporal difference, same thing, temporal difference. If you take a Lorentz transform, for example, you know, if you think the Lorentz transform for time, you know, in a primed frame looks like, what is it again? It's, what is it like? Oh, I can't remember it now. Is it just xc squared? I've forgotten it. I remember the distance one. I always forget the temporal one. It is... No, there's a... Ah, okay. Ah, yeah. Yeah, like that in with c equals 0. So if you have a, oh, sorry, there should be no prime here. Yeah, so if you have a spatial distance between these 2 points, like we do here, say this is the t in the x frame, and then the t prime frame is now this one. If you have a spatial difference between them, that will turn into a temporal difference between them, where the positions of the ends of the log will affect the times that you're measuring it at. But anyway, if we do the computation now, so we found the space-time interval in this frame, which is L squared, and if we find it now in the A frame, well, it's now going to have this component here. Professor Melko is raving with a party of 48. Oh, wow. Hello. Chemistry is greater than physics. That's quite offensive. Chemistry doesn't have time dilation in it, though, which is what we're currently talking about. No, that's okay. Disruption is totally fine. We were just, this is the office hour, so we're just talking about some general problems. We were talking about particle physics a little bit earlier, and now we're talking about relativity. So previously we were deriving the time dilation formula for clocks, how clocks that are moving very quickly through space move slower through time, and now we're deriving length contraction. So we were just talking about a problem, which is a pretty interesting one. So if you imagine you have a tunnel, I've spoken about this before, but because we got some chemists, I feel like maybe we need to go slowly. No, I'm kidding. If you imagine a train tunnel, oh, thank you very much for the follow. If you imagine a train tunnel that has got some length L. Oh, thank you again for the follow. Sorry, I missed the name of the last one. Tropical Tom, thank you very much. Oh no, someone followed. That means that we've broken the pattern that previously I had exactly 137 followers, which for a physicist is a very satisfying number. And for a chemist too, actually. Chemists can appreciate the fine structure constant. Oh, thank you again for Quantum Jerry 54. So let's get back to this tunnel. Imagine this train tunnel here has got 2 doors either side. These are pretty horribly drawn doors. And we set this tunnel up so that at some instant, these doors both simultaneously shut closed. Okay? And, you know, maybe they're very sharp, so if there's a train running through it, it'll cut the train in half a little bit. So now we think about, thank you very much for the follow, XOIIKU. So we think about this train coming through. Wow, this is a bad train. But anyway, this train, the point is this train is longer than the tunnel itself, okay? And it's moving with some speed v towards the tunnel. So there are a few ways of looking at this. Let's think about the perspective of someone that is standing on top of the hill. So they see the train running towards us at a very high speed. And what relativity tells us is that when something is moving very quickly, you actually measure its length to be less than you would if it was standing completely still. This is this phenomena called length contraction. So from the perspective of the green man on the hill, okay, thanks Prof Melko, thank you for the raid, very kind of you. From the perspective of the person that is, thank you for the follow, Cookie Diap. From the perspective of the person on the hill, if the train is moving fast enough, what relativity tells you is that, let's call the length of the train LT. It tells us that the length of the train that the green man sees is given by 1 minus the speed of the train squared over the speed of light squared times the length of the train when it stood still. So I've used the black length here to mean how you would see the length of the train if it was standing still, and the green LT is the length of the train as seen by the little green man. Not an actual alien, just happens to be a green man. Okay. So from the green man's perspective, if the train is moving fast enough, it can actually make it through the tunnel without being chopped into parts. Thank you for the follow, Ducati V4. Very kind of you. So that's what the green person sees. He sees the two gates on the train close simultaneously, and he sees the length of the train shrunk down. Thank you, Memish1903. So from his perspective, everything is fine. The train doesn't get chopped in half. Nothing goes wrong. Okay, well, what about for a little red man stood on the train? Maybe let's change the LT red to show that this is the length of the train as measured by the little red man that is riding on top of it. So he's riding on top of it, he sees the train as just being stationary. Okay. Well, from his perspective, he thinks he's standing still. So in relativity, there's no such thing as absolute velocity. Yeah, he should really duck. There's no such thing as absolute velocity. So it's just as well defined in relativity for the green guy to say the red guy is moving towards him, as it is for the red guy to say the green guy is moving towards me. Okay, let's ignore the fact you could see the wheels moving and you could tell. In a perfect sort of setup where you're in a lift with no windows or a car with no windows, assuming there's no kidnap going on, you wouldn't be able to tell the difference. Okay. So he sees the hill moving towards him. He doesn't see it as he's moving towards the hill. So therefore, surely he should see the length of the hill contracted. Okay. And he does actually. He does see the length of the hill contracted. But there's something else interesting that happens. He sees something else. So remember, the green person, he sees the two brown doors either side of the tunnel close at the same time. Okay. But the person that's on the train, the red person, he doesn't see that. He doesn't see these doors close at the same time. Okay? Simultaneity, things being simultaneous, is not a preserved thing in relativity. So whether you see something as happening simultaneously or not does depend on how fast you're moving, and, well, mainly just how fast you're moving, actually. So the red person here that is moving towards the tunnel, he doesn't see the doors close simultaneously. Okay, he sees them close with a sort of time difference between them. So if you imagine what the green guy sees, the green guy sees this kind of slightly squashed train, squashed because of length contraction here, because this thing here is going to be a small number. Because v is always less than c, this is always less than 1. So 1 minus it, you know, this whole thing is positive in here, so there's no square root of a negative, but it's going to be something that is less than 1. So the length of the train as measured by the green man is smaller than the length of the train as measured by the red man. So he sees this kind of shrunken train running towards the tunnel, and because of that, there's no issue. The train doesn't get cut in half. So when the train comes in, so the green man will see this sort of weird little squashed train with a little squashed red man on it. Well, he shouldn't be shorter, but he should be, you know, squished a little horizontally. And when the train is inside, then the doors smack down, shut for a second, and lift back up. So the train is not cut in half. The little red man is okay, and that's fine. But now if you think about what the red man sees, so he still sees his long train, and from his perspective, it looks like the tunnel is rushing towards him with some speed v. So he sees the little tunnel shrunk down. So he's thinking, uh-oh, there's no way I'm going to get in that tunnel and not get cut in half, because I am, you know, my train is much longer than this tunnel. So as soon as I get in that tunnel and as soon as the doors close, I'm going to get chopped in half. But remember what we said, simultaneity is not preserved in relativity. So although for the green man here, he sees these two gates close at the exact same instant and would chop anything that was there. But from the perspective of the man in, well, the red man, he comes towards the gates. He still sees his train as being very long because for him it's stood still. And what happens is, rather than the gates closing simultaneously, there's a time delay in when they close. So before the man has even got towards the end of the tunnel, this gate closes. Okay, it closes and then we say it sort of snaps shut for a minute and then snaps back up. So it closes. So he could now be inside the tunnel. But then it snaps back up. So now there's nothing that's going to cut him up on this side. So he moves a little further through. And maybe now he's here. And now the other gate decides to snap shut. Okay. So although these things appeared simultaneous in this frame, they're no longer simultaneous in this frame. So he still survives in both frames. And this is sometimes called a paradox because, well, surely this man would see the train getting okay because the train is shrunk in this frame, so there's no issue. But then surely this man here, who sees the tunnel shrunk, surely he would have an issue because now the tunnel is much, much shorter. So when the doors clamp down, it'll cut the train in half. But that's not the case because the difference in spatial distance between these points here translates into a difference in temporal distance between when these things close. Theoretical Phys 77, we will still derive that. Yeah, this was just a brief detour for the lovely folks that came from Prof. Melko's stream. Asher Adele says, but isn't the train also shrunk? Not according to the red man. So for the red man, from his perspective, the train is totally still. He's standing on top of it. You know, it's like if you imagine you yourself are in a train. If you can, when you're in a train that's moving at a constant speed, you can toss a ball up in the air, you can do whatever you like, and you've got no way of knowing how fast the train is going. It's only when the train is accelerating you feel something. Okay? So if the train is moving at a constant speed, a constant velocity, then there's no way of telling that he is that you're on a moving train. You can't tell the difference between not moving and moving at constant velocity. Theoretical Phys 77 says, could you elaborate on that time-space thing? I think there is something important there, like a deeper understanding. Well, it's all a consequence of the speed of light being constant. So, if you think about the fact that the speed of light is constant, no matter how fast you run at a light source, clearly something has to be going on there that is changing distances, changing how you measure distances, and changing how you measure times. Okay. So these things have to change in such a way that it will conspire to give the same speed to someone that is standing still with a light ray shining on them, and someone that is running very fast towards a light ray shining on them. And this is actually why when we derive the Lorentz contraction formula, it looks exactly like the time dilation formula, but instead of having a gamma factor, we actually have a 1 over gamma factor. And that's precisely because these things, this change in length that is observed due to motion, and the change in time that is observed due to motion, have to conspire in such a way that when you calculate the velocity of light, which you do by velocity is distance over time, that it should give you the same number no matter how fast you're moving. So we'll see that when we derive this Lorentz contraction formula, that it looks very much like the time dilation formula, except instead of a gamma, it's a 1 over gamma. Okay. I'll elaborate on the time and space thing. Well, so yeah, I guess that's a sort of comment on it. But the more general thing about saying how a difference in spatial distance translates to a difference in temporal distance. So here, the fact that there was a spatial distance between the two ends of this tunnel, which in the frame of this person here that was moving very quickly towards the tunnel, translated into a difference in temporal distance. So now, instead of slamming shut simultaneously, as they did for the green man here, what happened is these gates shut, this one shut first, and then it opened up again, and then this one shut. So it translated into a temporal distance between them. And this is all to do with Lorentz transformations. We wrote down a Lorentz transformation slightly earlier. So you can see how a spatial difference here translates into a temporal difference as measured by someone else. So for those that joined from Prof. Melko's stream, we were just finishing off a derivation using space-time diagrams. We were looking at this setup where we have a man on a train with a log, and he's observed by someone that is standing just on the ground and is watching this train here speed off with some speed v. So this is from person A's perspective, which is why person A is highlighted here. And alternatively, from person B's perspective, from the perspective of the person that is just sat on the train, they now see this log as stationary, and they measure these two ends simultaneously, the two ends of the log. And rather than seeing person A as stationary, they themselves, from their perspective, they are stood still, and it's person A that is whizzing away with a speed v. So person A sees person B moving to the right with speed v, and person B sees person A moving to the left with speed v. Okay? And we defined this length L here to be the spatial distance that person B measures between either end of these two logs. Okay? I mean between either ends of this one log. And we plotted this on a space-time diagram. So here is the space-time diagram from person B's perspective, where they measure the two ends of this log simultaneously, and they have some distance L between them. And then from person A's perspective, so person A is the one that sees the train speeding off to the right with a speed v, we plotted person B's space-time axes on this graph. And this means you need to know, knowing how to do this means you need to know a little bit about special relativity, which we didn't go over too much, why this is the case. And this angle is given by, or rather tan of the angle gives the velocity. So we calculated the space-time interval on this diagram as being purely due to this delta x component. The space-time interval is, oh, there should be a squared there. Instead of being just a normal Pythagorean distance, like a delta x squared plus a delta y squared, down here, sorry, I realise my chat window kind of blocks it a little bit. It has a minus sign in front of the time component, okay? So we calculated it in this frame as L squared, and now we were just about to calculate delta s squared from person A's perspective. So let's do that. We need to find the temporal and the spatial distance between these 2 points here. Okay. So let's do that. So we have that tan theta is equal to v. So if I call this distance here delta x a, well, then if this angle I've got drawn here, let me draw it in pink, this angle theta here, tan of it is given by v, then I can work out the temporal distance between these two red points. So the distance along the t-axis between the two red points as being, where have I drawn it? There we go, delta t a. Well, delta t a, just from trigonometry, is tan theta times delta xa, or in other words, is v times delta xa. Okay. So if we put that into our formula for the interval, where we have a minus delta Ta squared plus delta Xa squared, that turns into a minus delta Ta squared. Well, hang on, no, sorry, let's do it in terms of Xa. Oh, hang on, have I made an error? Tan theta is... No, I think that's okay. Yeah. Then we have 1 over v squared delta x a squared minus that, sorry, plus delta x a squared. Okay. Maybe we have made a slight error here somewhere. This should be a v squared here. Have we done something wrong? So these angles are both theta, that's true. And tan of theta is v. So why does that give us 1 minus 1 over v squared, when it should be 1 minus v squared? What have we done wrong? Can anyone spot what we've done wrong? Is that angle there the same? I'm pretty sure this theta here is the same as that theta there. So... Yeah, we've made an error somewhere. What have we done? So we should have L squared. Yeah, I think it should be 1 over v squared though. Because tan theta is still given by... Tan theta is still v, is the thing. Oh, well, yeah, that does... I mean, I agree that delta x is given by that. As in, just in terms of distance, you know, is speed times time. But then I'm a little confused now, because if you just think about it in terms of a triangle, we've got a triangle here where the opposite side is delta t, the adjacent side is delta x, and the tan of that angle, theta, is v. Okay, well that's a... I see what you mean. That's a problem for another day. Well, okay. Yeah, let's do that. So we have delta x is v delta t. Okay, so we did make a slight error there. Wait. No, hang on. What was I... No, the thing I had just then I think was okay. So I said... But yeah, I did the substitution wrong. Oh, I see what you mean. Yeah, right, no, we were okay. Yeah, okay, sorry about that. We plugged in the 1 over v fine. Okay, that's all right. So that's delta x a squared 1 minus v squared. And that is what this interval here is equal to. And that is equal to the interval here as measured by b. This is going to give us it the wrong way around, though. This is going to tell us that xa squared is gamma times L. when it should be 1 over gamma times L. Ah. Okay, I think we have made a slight error in working this out. So when person A measures the length of something, when you measure the length of something, you have to try and measure the length simultaneously to get a measure of the length. But when they measure the different ends simultaneously, that corresponds not simultaneously to person B. Okay, so they're actually measuring different space-time positions when they do it. So the intervals are not the same because actually it's a different event on the other end of the log that person A is measuring. Okay, we'll have to fix that. Well, once again, we will leave that for next time and we will fix it next time. Because I've run over a little bit, but that's okay. What was this? Speaking of paradoxes, if the existence of a minute universe allows a space shuttle to go in a circular path, barely touching the tip of the booster end, would the spaceship wrap around the universe and destroy itself? Wait, what? If the existence of a minute universe allows a space shuttle to go in a circular path, barely touching the tip and the booster end, would the spaceship wrap around the universe and destroy itself? I'm not totally sure I understand the question there, Alan MD. Oh yeah, I see what. Yeah, so when person A measures it, that's right. They have to measure it simultaneously to measure the length. So we just have to construct on our diagram a way that he would measure two events simultaneously at the ends of this log. But like I say, we'll do that. We'll do that next time. We'll look at that on Friday, I believe. But yeah, let's leave it there for now. So if you haven't already, please do consider joining my Discord, which I will... Oh, thank you, Jeg Chin, you beat me to it. Yeah, please do join my Discord. We can talk more on there about this problem. And you can submit questions for the other office hours on there too. But yeah, we'll finish off that not time dilation, sorry. We'll finish off the length contraction next time. Thank you to all of those that followed today. Much appreciated. Tomorrow, today's Tuesday. On Thursday I'll be playing some Mario Kart again. So feel free to come to watch me play some Mario Kart and have a bit of a physics chat. But okay, we'll leave it there anyway. Thank you all for joining. See you, some of you, on Thursday. Okay, bye.